This is Professor Brothers, and I'm going to go over an example software design. This is for ECE Design Fundamentals. This lecture is going to focus on walking through the software design process to better understand the output products. Specifically, we're going to look at a state diagram, software architecture, and a software framework, also known as the skeleton code. We're going to do this by looking at an example system and the output products associated with that example system. For this example system, let's assume that we are working for an engineering consulting company, and that engineering consulting company has been hired by Farmer John. So Farmer John is looking for a system to design and install an irrigation system for his farm. We're going to start on the top left of the V design process. So here are Farmer John's needs. Only water at night, only water if it's not raining. Shut off the system if the temperature falls below freezing. Water each zone for 20 minutes every day. The system should be able to support 10 zones. Must be able to configure watering times from an internet page from Farmer John's house. Must be able to turn on a 120-volt, 3-phase water pump. And must be able to enable the water solenoid valve for each zone. So let me take just a second and talk about these needs. We can assume that at Farmer John's house, he has access to the internet. But then at some geographical distance away is his well house. And at the well house, he has the 3-phase 120-volt pump, and he has the water solenoid. These are what actually will work as a water valve, an electronically controlled water valve to allow water to flow out. The pump does not run all the time. So when we need to actually start watering, we first have to turn on the pump and then open the water valve. Now, one of the big considerations, this is on a farm in a very remote area. So we cannot assume that there's connection between the house and the well house. They are some large geographical distance apart. They might not have cell service. They might not have internet service. We have to consider how we're going to communicate from those two geographically discrete locations. So here is the state diagram, and this state diagram is going to be running on the controller that is located at the well house, okay? And we're going to work on this example a little bit more on class in order to do the requirements breakdown and a subsystem breakdown. But let's assume that this controller controls the physical location of the well house. And at that well house, we have a rain sensor, we have a local schedule that is maintained on the system. And then in that local schedule, it dictates which zone is going to be watered. So if we lose the connection to the internet, we still have a local schedule and we can keep operating. And if something changes on the internet website, it's going to be sent down in this user input command. So let's go over the state diagram real quick. We start off in the idle state. And sitting in the idle state, let's say that we get the user input command indicating that something has changed on the website. We update the watering schedule and then return to idle. While we're sitting at idle, there is a timer that's running. And with this timer, we can check and see if it corresponds to any start time. If it does, we'll go into this loop and it will water zone in for that set 20 minutes of time, and then it's going to turn off. Every so often, we're going to pull the rain sensor. So we're going to look at the timer and we're going to look at this rain polling value. And so every so much amount of time, we're going to check the rain sensor to see if it's raining. If it is raining, we're going to update the schedule with a rain delay and return to idle. If it's not raining, we're just going to return to idle. Now, this is not the best state diagram. This is an example state diagram. And as you go through this example in class, think of how you could make this better. But this is only for example's sake. All right, so from there, we go into our software architecture. The state diagram lives in the state machine manager block. This is the brains that controls this chunk of software. And then you can think about it that there are certain classes that are going to be servicing what needs to be done according to what the state machine manager tells it to happen. In this instance, we have the user web interface class, the scheduler class, the rain detection class, and the water controller class. Each one of these classes is going to have a set of functions underneath it. For user web interface, we have the user input, and we saw that user input being used in the state machine manager. So that is going to alert the system that there is some user input change. In the scheduler, we have get schedule, set schedule, rain delay, and get time. The timer is, we can infer, is also located under the schedule from this. The user web interface class has the ability to call the set schedule function. So if there's a user input flag, the user web interface class can call the set schedule and update the schedule inside the scheduler. The scheduler has the ability to monitor the user inputs. It also has the ability to monitor get rain and water zone in. So the scheduler is kind of the main class, and everybody else is underneath it. Rain detection, get rain, can be called from the scheduler. And then water controller, which has water zone in, can be called from the scheduler. And then water controller can call get time to see if the correct amount of time has elapsed before it shuts off. So you can see how these different classes can interact with each other, and they have different functions that are servicing different needs within this community. And then there is also a get schedule and set schedule. We might not use get schedule all the time. This might just be used in the future expansion. So we also want to design this with hooks for future interfaces. That brings us to the software framework. This is where we're now getting down to the nuts and bolts of actually programming it. So we've started off with our broad idea, which was the state machine, of how the system's going to, in a broad stroke, work. Then we narrowed that down a little bit more, made it a little bit more concrete with the architecture that's showing the different classes, the different functions that we might need. Now the software framework is where we start to implement those classes and functions. So you can see in here we have a user web interface.h, scheduler.h, rain sensor.h, water controller.h. All of these files need to be created. All of those files need to be populated with a dummy class that just has an empty function prototype as defined in the architecture. Then this has the main, and here's where all the classes are created. And this next comment says the state machine is below. So the state machine is going to be located in the main loop, and it's going to run, and then the classes will be created and called as need be inside that state machine. So all of the structure is built in the framework or the skeleton code, but most of the function prototypes will be empty at this point in time. Save this off to Git, Bitbucket, GitLab, Subversion, whatever repository management system you want to use or version management system you want to use. Then allow your team members, the people that are working on this project for you, to write into those given files. And if you organize it in this way, the whole team can work on the software simultaneously without stepping on each other's toes, because every member of the team will have their own file that they're going to update and work on. So in this manner, you can break a software task up and have it effectively worked on by a team, have it effectively tested by a team, have it effectively maintained by a team once it's deployed. All right, I hope you enjoyed this video. Let me know if you have any questions.